My name is CHARANYA TANABALAN. My metric number is 17DKA 24F1020. The objective of this test is to determine the optimum bitumen content in the mixed bearing cores and binder cores in designing the pavement structure of flexible pavement. Secondly, the theory of this test is flexible pavement design consists two main elements, that is design thickness and mix design. The design thickness is related to the semester 6 syllabus, which is designed based on Road Note 29. Mix design is focused on the mixture of substance used as binder layers and wear layers. These materials must be through a proper mix design. There are various methods of mix design, but the Marshall mix design method is most popular. Apart from determining the optimum bitumen content, this method can also specify aggregate grading on the most suitable mix design. The Marshall method outlines the procedure beginning with specimen preparation until the determination of optimum bitumen content. The apparatus for this test is test machine Marshall, head of steel test, water bath, extrusion jet, Marshall compactor machine, oven, and lastly is weighing scale.
Firstly, preparation of specimen. Aggregates and fillers that will be used are determined. The mixture comprises sufficient aggregate, sand and filler to produce a specimen of approximately 1200 gram. Preheat the aggregate in oven at 150 Celsius for at least 4 hours. Heat the bitumen at the same temperature or the temperature of the mixture. Number 4 is the hot aggregate will be heated again in bowl. Heat without adding any bitumen, mix for 1 to 2 minutes. Then add the correct amount of bitumen. The bitumen content that is used is the percentage of weight of the total mix. Number 5, the temperature during the mixing of aggregate bitumens. Mixture should not be below 137 Celsius. Number 6 is, while preparing the mixture, the ram and Marshall mold should be cleaned and heated to 137 Celsius. Number 7, put the mold on the table and put a piece of filter paper into the mold. Pour the hot mix into the mold and smoothen the top surface. Then put another piece of filter paper. Number 8, place the molds on a pedestal and compact on both top and bottom surface of 55 blows, which designed for maximum tire pressure 0.75. Number 9, remove the collar, leave the specimen for a while as the second mixture is prepared and take out the specimen using an extrusion jet. Let the specimen cool before testing it. To test the specimen, first weight and record the specimen's weight in the air. Then weigh the specimen again by putting it in water and record its weight. Calculate the unit weight of the specimen. Second, heat the specimen in the water isotherms water bath at 1 Celsius for 30 to 40 minutes. Number 3 is clean the surface of the head tester. Put the specimen in the middle of the head. Fix the head on the correct position of the tester. Number 4 is place the head tester equipped with the specimen on the pedestal of the Marshall testing machine. Last is switch on the record the maximum force and maximum power flow.
Now this slide contains the data we have gotten from our test. The table contains the volume of specimen, which is in cm per cube. Then we have approximate thickness of specimen, which is in millimeter. Then lastly we have correlation ratio. Now let's look at the discussion. The table provides a clear relationship between the volume and approximate thickness of the Marshall test specimen and the required correlation ratio for adjusting stability values. As both volumes and thickness of specimens increase, the correlation ratio systematically decreases, indicating that smaller specimens tend to give artificially high stability readings, while larger specimens tend to underreport stability. Notably, the highest correlation ratio of 5.56 to is observed at the smaller specimen volume range, which is 200 to 213 cm per cube. Thickness is 25.4 millimeters, and it gradually decreases to 0.76 at the largest specimen volume range, which is 611 to 625, and thickness 76.2 millimeters. The standard reference point is set at specimen volume of 509 to 522 cm per cube with a thickness of 63.5 millimeters, while the correlation ratio is 1, meaning no correction is needed. This relationship underscores the importance of applying the approximate correlation factor to ensure the Marshall stability results are consistent and comparable to across different specimens sizes, thereby maintaining reliability of bituminous design mix design evaluations.
Hi, my name is Muhammad Adam bin Muhammad Sadi. So, the conclusion for the Marshall stability test, when corrected using the provided correlation ratios, enables engineers to accurately evaluate the load-bearing capacity and deformation resistance of asphalt mixtures. Based on the table, smaller specimens require significantly higher correction factors, sometimes over 5 times the standard, because their measured strength is exaggerated due to size effects. In contrast, the larger specimens yield stability values closer to the true value, needing only minimal correction as the ratio approaches 0.76. The standard specimen with a thickness of 63.5 mm and a volume of 509 to 522 centimeters cube serves as the benchmark for uncorrected, reliable stability readings. Therefore, carefully specimen preparation and correct application of the correlation ratios are essential to obtain valid and comparable Marshall stability results, supporting the proper design and adjustment of asphalt mixes to ensure long-term durability, resistance to rutting, and reliable performance under traffic loads.